Louis de Broglie advanced the philosophy of quantum mechanics by creatively equating Einstein's energy-momentum relativity formula with the Planck-Einstein relation. As previously outlined, there are several issues with the development of the Planck-Einstein formula. Special relativity also suffers from the single observation angle of the Lorentz factor. Relativistic mass, as a failed proposition, has equally disqualified the enthusiastic application of the Lorentz factor to non-information realms. Nevertheless, quantum mechanics had picked up enough scientific momentum to be defended and expanded. De Broglie's philosophical explanations were creative. Wave-matter duality was a philosophical stepping stone, allowing the new science of quantum physics to transition from the hard particle model of Bohr's two-dimensional quantum theory 1 to the probabilistic model of three-dimensional wave equation quantum theory 2. This transition pushed the hard science of physics into the ethereal realm, where observations and understandings are often categorized as simply weird. But first, the math. Schrödinger, Heisenberg, Born, and others developed rigorous mathematical treatments, expanding on the model proposed by Bohr to create the three-dimensional excited state atom that exists today. The complicated mathematics uses Hamiltonian linear operators with discrete solution eigenvalues. It respects Bohr's treatment and preserves his ground state radius of hydrogen as the highest probability location within the probabilistic model. A mathematical solution for the Hamiltonian is only available for the hydrogen atom. Two electron atoms need computational approximations. In this model, new quantum numbers are used to explain different orbital energies, conforming to the electron categorizations in the periodic table. The principal quantum number is the periodic table row number. Azimuthal and magnetic quantum numbers identify the p and d electrons in the old SPDF model. The result is a probability space atom, where the sole electron exists anywhere in a spatial cloud. Here, the 1s, 2s, and 3s orbits are shown, even though hydrogen only has a single 1s electron in its atomic form. This is the radial node arrangement. Assigning hard physics parameters to an idea so ethereal is problematic. An electron is assumed to be darting around in this space, constantly changing directions, accelerating and decelerating with no known rational explanation. A particle could not carry out this operation without requiring constant energy input. With constant energy input, the only way to dissipate it is through radiation, which it clearly does not do in a steady state. Therefore, the electron must take on some massless state and become massive when it is measured. The electron is a wave until it is cornered by a laboratory technician. Even when cornered, all the electron's characteristics cannot be stated with certainty. The Heisenberg uncertainty principle codifies this dilemma. The measurement phenomenon in the quantum model opens a can of worms whose resolution requires philosophical treatises, such as the Copenhagen interpretation. Nowhere are these concepts more demonstrated than in the multiple iterations of the single and double slit experiments. These experiments, some with light and some with electrons, all seek to magnify this philosophy. They do not consider the edge effects of EM waves or electrons passing through the tiny metal slits, interacting with electrons on the sides of those barriers as they pass through. The hydrogen atom takes on the excited state probability space of all electrons identified in the periodic table in an energy hierarchy. So even though the hydrogen atom only has one electron, it can be promoted to, for instance, the hypothetical 3p orbital track. The p orbitals are separated into planes in this mathematical treatment. Nodal employment can be radial, planar, or another form. The following is a summary of quantum theory development. Boltzmann modeled individual atoms in a statistical ensemble, effectively isolating the smallest element that could not be further divided. The Maxwell-Boltzmann distribution used equipartition of energy theory to accomplish this. There is no way to assess individual particle velocities to verify this assumption. Planck built upon the work by Wien and others to apply the Boltzmann technique to atomic radiators on the interior surface of a blackbody. The blackbody radiation spectral intensities yielded individual atomic behavior cues that were unavailable to Boltzmann in his assessment of velocity distribution. Planck altered the exponential form used in Boltzmann's distribution. He assigned an energy mode to each of his elemental radiators, implying a quantized radiation energy and the standing wave reflection patterns in the blackbody. Einstein adopted and adapted Planck's radiator formula in his explanation of the photoelectric effect experiment. He worked both sides of the equation in his explanation. Electron liberation was described by a work function, which has no scientific value other than its use in this model. The result is that each wavelength of light was packaged into a minimum energy formation. That package, later named a photon, was given particle status with effective mass via mass-energy equivalence and momentum via the energy-momentum relation. Bohr created the orbital atom. He used centripetal force versus Coulomb force for orbital analysis. He adapted the Rydberg formula to determine the orbits of electrons. This incorporated a large number of assumptions, leading to the abandonment of classical physics principles. DeBroglie opened up the philosophy of atomic construction to the probability space description. His primary assumption is that all moving bodies have an effective wavelength. Wave equation quantum mechanics was developed, bringing probabilistic philosophy to atomic physics. Solutions to the wave equation required the collapse of the wave function to isolate a particle's properties. The uncertainty of a particle's location and momentum in probability space was the net result. The wave equation is so limited that it can only characterize single electron atoms. Ultimately, like general relativity, theorists labor to further quantum mechanics without scrutinizing the foundations of the science.